Thank you very much for the kind introduction, and first of all, thanks to the organizers for giving me this opportunity. So as you heard, I'm Andrés from Imperial and Queen Mary, and I would also like to acknowledge the two funding agencies, the European Commission and the Royal Society. You already heard the title. So the main result of this work is that we found a laser field configuration which is able to drive this electronic transition much more efficiently in this enantiomer than in the opposite enantiomer, while taking into account that the molecules are randomly oriented and randomly positioned across the interaction region. We do that using a coherent control approach, and we do it in a molecule which is called carbon, which has some interesting photochemistry. Basically there, when you when you have this electronic excitation, it triggers a very important type of photochemical reaction of photoisomerization known as photocycloaddition. So because the electronic excitation is the first step of a photochemical reaction, then by selecting whether we excite this or this, we also select whether we drive this photochemical reaction or this photochemical reaction. And that is the take-home message of this talk. And in the rest, I will just try to give you some more context and some more details of how this works. So I won't introduce chirality. It has been already mentioned in previous talks. It is prevalent in living beings. It is also very important in nanotechnology, for example, molecular motors, spintronic devices, self-assembling structures. So yeah, chirality is an important thing. Now, what makes the manipulation of chiral molecules difficult or challenging? Well, one of the most important ideas in physics is the realization that different systems have different energy spectra. And we rely on that knowledge, for example, to selectively excite molecules in mixtures. So for example, we could have this molecule surrounded by water, and we could excite this without exciting all the water around it by just selecting the right photon energy. But now, what if the mixture has two different molecules, but these two molecules differ from each other only by a mirror reflection? Well, in that case, they share the same energy spectrum, and we cannot just use the right photon energy to excite this more than that. So instead, we have to rely on using the chirality of light. Just like a right-hand glove fits a right hand, but not a left hand, then chiral light of a given handedness will excite more one enantiomer than the other. Circularly polarized light is, of course, chiral. It makes this helix in space. But the problem is that the helix has a characteristic scale given by the wavelength. And the wavelength for an optical transition is hundreds of times bigger than many chiral molecules. So basically, the glove is too big for the hand. And that is the, let's say, physical picture of why circularly polarized light is not well suited to selectively excite this molecule, but not its mirror image. Nevertheless, circularly polarized light does have some selectivity, so maybe by understanding the details of how it works, we can figure out a better way to have selectivity. So in the one photon case, to have enantioselectivity, we need to include the electric dipole and the magnetic dipole transitions. So the population in the excited state will have contribution from each of those, but also from their interference. And it turns out that if you do the math, which means doing some perturbation theory and some orientation averaging, because the molecules are assumed to be in the liquid or in the gas phase, then you get this expression, where the first scalar product between the electric dipole and the magnetic dipole has opposite signs for left and right-handed enantiomers. So it encodes the molecular chirality, and the second scalar product between the electric field and the magnetic field has opposite signs for left and right circular polarization. So it encodes the chirality of the field, more specifically the helicity of circularly polarized light. So basically, this interference term is the one that is coupling the molecular chirality to the field chirality, and this is what explains enantioselectivity with circularly polarized light. That's very nice. The problem is that the electric dipole transition is usually much stronger than the magnetic dipole transition. So basically, we get interference, but with very, very low contrast. So we have a lot of background from this. And that's the reason the enantioselectivity is very low. But we can solve this very easily. Instead of relying on the magnetic dipole, we rely on a two-photon electric dipole transition. And the key here is that since we have different frequencies, and we can control their intensities independently, then we can balance the interferometer. So we can make this pathway just as strong and as the other pathway. Now in this case, if you do the math again, then you get this expression for the interference. So instead of the magnetic dipole, now you have a cross product between the two electric dipoles, and instead of the magnetic field, you get a cross product between the two electric fields. Again, this part encodes the molecular chirality, and this part encodes the field chirality. But this is a different type of chirality. As you can see here, to make this non-zero, because it is a triple product, we need the three polarizations of these frequencies to be non-coplanar. For example, we could use these three frequencies, omega, 2 omega, and 3 omega, linearly polarized, perpendicular to each other. And actually, if we draw the Lissajous figure of the total field, it would look like that. So this red arrow is the electric field, and as time goes on, its tip traces this twisted Lissajous figure. So what I want you to notice here is that here, with circularly polarized light, we also have a twist, but the twist is as a function of position. Whereas here, the twist is as a function of one of the field components. Yeah, so this is a fundamentally different type of twist, and we call this locally chiral light, and we explore it in a series of papers. The important thing is that this type of local chirality, that's how we call it, local chirality allows us to basically balance the interferometer. We are not the first ones to study the problem of coherent control in chiral molecules. There are very important theoretical and also experimental works. One of those was briefly mentioned this morning. And actually, the experiments so far work in the microwave domain. So now we want to do something similar, but in the directly for electronic transition. So what we do is that we start with a sample which is racemic, meaning it has same amount of left and right-handed molecules, and it is isotropic, so randomly oriented molecules. Then we excite that sample using this laser beam configuration, where we use frequencies omega, 2 omega, and 3 omega. Here the 3 omega is to be understood linearly polarized perpendicular to the screen. And we solve the time-dependent Schrödinger equation, do the orientation averaging, all of that, and we look at the population in the excited state. And we do that for the left molecules, then for the right molecules, and we compare the excited state populations in left and right-handed molecules. So basically, we take the difference and divide it by the average. So if that number gives, for example, 8, it means that right-handed molecules are 8% more likely to be excited than left-handed molecules. And if we get -8, it means the opposite. So left-handed molecules are 8% more likely to be excited. So basically, in the blue regions, you get more left-handed molecules in the excited state. In the red regions, you get more right-handed molecules in the excited state. So first of all, the fact that we get this kind of number, like almost 10%, is already very good. With circularly polarized light, we would only get like 0.01% for this particular molecule and for this transition. So it's already almost 3 orders of magnitude improvement. The problem, however, is that we have this variation as a function of position across the interaction region. And this is occurring on the scale of the wavelength, which here is of the order of 1 micron. So it is the selectivity is oscillating really, really fast in space. What this means is that if we do the average in a regular experiment, we will lose the selectivity. Yeah? We have the same amount of red and blue. Why is this happening? This is happening because imagine we have plane waves for each of the colors. Then, so we have an amplitude, a polarization, and a phase. Then the chirality of the field, which is the expression that I introduced in the previous slide, looks like this. And it is a product then of 3 plane waves. So it yields another plane wave. And this new plane wave, which basically describes the enantioselectivity, has an amplitude, which is given by the triple product of the polarization. But more importantly, it has this wave vector, which is given by k1 plus k2 minus k3. So basically k1 coming from this, k2 from this, and k3 from this. And the reason this goes down is because it's complex conjugated. So we get this delta k, which as you can see agrees with the direction of this oscillation, and it also has a magnitude which is of the same magnitude as K1. So it also explains why it oscillates on this scale. Now we could deal with that, for example, by confining the interaction region to one of these stripes. We could do that, for example, using liquid jets, but still you need to know how this is changing in, yeah, I think I lost my pointer. So it will be difficult. Anyway, you need to know how it changes, and you need to position this very precisely. So what we did was that instead of considering 1 versus 2 photon coherent control, we consider also the case of 2 versus 3 photon coherent control. And in this case, basically what we obtained, I think this died. Yeah. Yeah, so in this case, what we obtain, again, we solve everything, and what we find is that we can keep the enantioselectivity basically constant across the interaction region. So you see it's varying between 27 and 27.4%. And the key to do that is that now for this excitation scheme, for this 5-photon process, the mathematical derivation of the field chirality, so the interference term, has a slightly different expression. So again, a triple product, but now also a scalar product. And the important part here is not only that we have this extra scalar product, the important part is now that the wave vector has this form. So now we have K1 plus 2K2 coming from the 3-photon pathway, so K1 plus K2 plus K2, minus K1 minus K4 coming from the other pathway. So as you can see, the K1 will cancel exactly. And the 2K2 minus K4, if you neglect dispersion, it will also cancel. If you don't neglect dispersion, well, it will give you a small number that will lead to an oscillation on a scale much bigger than the wavelength anyway. So basically, we can get rid of the those oscillations of the enantioselectivity across the interaction region, and we still have control. And now the control is given by the relative phase between the 2 omega and the 4 omega. So here I just want to summarize. So what we want to do is this enantioselective photochemistry, and we do it by controlling the excitation. If you use circularly polarized light, you have very little selectivity. If you use, let's say, the simplest coherent control scheme, you get good selectivity, but it oscillates as a function of position. And if you use this 2 versus 3 photon scheme, then you can get rid of the oscillation in space. And with that, I finish. Thank you for your attention.
Thank you very much. The talk is open for questions.
So thank you very much. Very nice, very interesting. This, I mean, I would think this trivial scheme, the better solution would have been, or the more straightforward, to just use completely different wavelengths or something, completely different K vectors. It is actually very interesting that using the, in principle, seemingly way more complicated schemes with more photons works so much better because it's mathematically so much nicer.
Yes, there are several ways that you can get around this oscillation. So one of them is using a much smaller, a smaller wavelength, longer wavelength. The problem, but yeah, you may have problems with that in the sense that you may start. I would have to check. Anyway, we wanted to do it like omega 2 omega and 3 omega because this is very easy to generate using harmonics.
So this point, this volume averaging point was overlooked for a while, I think, when people discussed this. I mean, they didn't realize it, and this is why the microwaves have an advantage, right?
Absolutely, absolutely, yes.
Okay, one more question, if you have any. Okay, if not, thank you again for a nice talk.